vector potential. Okay, chapter 2. We got curl of E equals 0. Do you remember that? In this chapter, divergence of B equals 0. So in here, we introduced E as minus del V, where we called E as the electric field and V as the potential, correct? So V was potential, and E was the electric field. Now, in this case, we are allowed to do something similar. We are going to introduce another term called A, which we are going to call vector potential. Note, in one case, the curl of E was 0. In the other case, divergence of B equals 0. Both lead us to potentials. In one case, it will be a scalar number, and the other case, it will be a vector number. Vector potential. Now, there's a third way of writing Ampere's law, and I'll show you how that works. Another way of writing Ampere's law. I'm going to start with mu naught J. That's our standard way of writing Ampere's law from this star equation. May I plug this in here? What will I get? Del cross A equal mu naught J. Going back to chapter 1, this is a curl of a curl of A, right? A curl of a curl of A was number 5 in our table that we drew for chapter 1. I'm going to go back to chapter 1. That's the first one. Second derivative, this was it. Here we go. There we go. It's from that big chart. So it was number 5 here, right? It was a curl of a curl that gave us the gradient of divergence minus the Laplacian. So this is going to come back. So that means I can rewrite this as the gradient of A minus Laplacian of A. So this part is the gradient of divergence, and this part was called the Laplacian. And what was the gradient of divergence? 0. So I am reduced to Ampere's law in terms of vector potentials. Woohoo! Oh, I was supposed to make a smiley face. And anyone remember what we call this? This is nothing other than Poisson's equation. And the solution of this Poisson's equation is, drum roll, it's going to seem so familiar once I write it down. The most general form in terms of J's. Volume current densities. So for volume currents. Can you guess what it will be for surface currents? And also for line currents. So for surface currents, it'll be mu naught over 4 pi integration K dA and for line currents, it'll just be mu naught 4 pi I R dL. See, if you look at them individually, if you don't know where things are coming from, they look really, really complicated, don't they? At least they do to me. But like once you see them all written out together, you see the similarities between the stuff, and then they don't seem any scary anymore. They don't seem like, oh my goodness, where did this scary looking formula come from? It's actually just 1, 2, 3, 4. It just flows naturally.